Oh no, absolute values. That's okay. They're not so bad. We have two absolute value expressions to solve here. We're going to look for their solution sets. There's only one variable involved, x, and so any description of the solution set to these inequalities will live only on a straight number line. We don't even need a two-dimensional coordinate plane. The best way to tackle any of these, we'll do this for this one as well as this one, is to try to isolate the absolute value expression. So we have the absolute value of something something, greater than or equal, less than or equal, greater than, less than, whatever. And then all the other junk that isn't in the absolute value. What that means is up here, I would like to first isolate the absolute value of 3x minus 7, have that on one side of the equation, and all the other junk on the right side of the equation. Here, that means we're just going to add 5 to both sides. Oops, straight bar. Okay, down here, that means we need this 3 to hop over there. So we're going to subtract 3 from both sides. Now we have less than on the top, greater than on the bottom. That's not really a problem just yet. Let's think about what this means. There's two things that this means. Let's think about what this statement tells us. Because absolute value bars are great as a notation, but you cannot inflict algebra on the thing inside absolute value bars with those bars in the way. So we have to learn what this expression means and write it in a way that does not involve absolute value bars. I've drawn a number line and I've put 11 there. If the absolute value of 3x minus 7 is less than or equal to 11, can 3x minus 7 itself live on this part of the number line? Well, no, it can't, because if 3x minus 7 is greater than 11, then the absolute value of 3x minus 7 will be greater than 11, so we don't like that. Could 3x minus 7 live right here? Well, sure it could, because if the size of 3x minus 7 is less than 11, let's say 3x minus 7 was 8, well, that's less than 11, and the absolute value of 3x minus 7 would be less than 11, and so that's good. But there's a limit to how far we can take that, because once we get down here to negative 11, if 3x minus 7 itself lived anywhere in between 11 and then down to negative 11, the absolute value of 3x minus 7 would still be less than 11. But let's say the 3x minus 7 lived right there. Pretend 3x minus 7 was negative 12. The absolute value of 3x minus 7 would not be less than 11, and so once again, we're out of luck. So if the absolute value of 3x minus 7 is going to be less than 11, that means that 3x minus 7 itself needs to live between negative 11 and 11. And we can write that with what's called a compound inequality. We just recognize at the same time that negative 11 needs to be less than 3x minus 7. Negative 11 is a left bound for this stretch of road. And at the same time, that 3x minus 7 must be less than 11. So we just put that all together into an inequality that has two inequality signs. Oops, and I should put the equals back in there. But now the absolute value bars are gone, and now we can inflict algebra on this thing. The philosophy is still what it always is, which is we would like to isolate the x. It's just that here, the x is going to be isolated in the middle of a compound inequality, but that's fine. That's all right. To get from here to there, you just do what you would normally do. To start digging into the x here, we want that negative 7 to go away. That means we are going to add 7 everywhere. Every little pocket of this compound inequality, we're now going to add 7 to it. So negative 11 plus 7 gets us negative 4. 3x minus 7 plus 7, we're down to 3x. 11 plus 7 is 18. And then we're going to divide by 3 everywhere, and I left a little too much space because now we're already ready for this. If I divide across the whole thing by 3, I will get negative 4/3 on the left. 3x divided by 3 is just my x, and then 18 divided by 3 will be my 6. And so what this means is, if we want the absolute value of 3x minus 7 to be less than 11, or to solve the equation above it, then x itself has to come from between negative 4/3 and 6 on the number line. And so there, let me put it in the origin this time. Here's negative 4/3, here's 6. X itself can be negative 4/3 because of that equal sign. It could be 6 because of the less than or equals, and it could also be anything in between. And that's a visual representation of our solution set. Now, down here, this inequality is a little bit different. We cannot just write this as a compound inequality in one shot, because there's two parts to it. If the absolute value of x plus 4 is greater than or equal to 4, then x plus 4 could live out here, right? It could not live here. Let's put down the origin. X plus 4 could not live here for small negative values close to 0. Say at negative 1. If x plus 4 was negative 1, the absolute value of x plus 4 would not be greater than or equal to 4. But then we flip the switch again when we finally get to negative 4. If x plus 4 is, say, negative 10, then the absolute value of x plus 4 would be 10, which is greater than 4. So what we've discovered is that if we want the absolute value of x plus 4 to be greater than or equal to 4, then x plus 4 itself could already be greater than 4, or it could be down here on the number line at values less than 4. These two regions are disconnected, so we can't just write them in one shot like we did up here where the whole region was connected. So two different regions that are disconnected, and so what we need to do here is take this absolute expression and rewrite it as the two options. Well, if the absolute value of x plus 4 needs to be greater than or equal to 4, then x plus 4 itself could be greater than or equal to 4, or the x plus 4 could be less than or equal to negative 4. And I'm going to put some brackets around that just to keep them grouped. Now each of those is pretty easy to solve. This top one here, if x plus 4 is greater than or equal to 4, subtract 4 from the left and from the right. That means x could be greater than or equal to 0. Or, and now we tackle this one. To solve this for x, let's subtract 4 from both sides of the inequality. And so now we've discovered that if we want this mess to be true, which means we want the absolute value of x plus 4 to be bigger than or equal to 4, that means there's two options. X itself could be greater than 0, or x could fall less than or equal to negative 8. And to describe that particular solution set on the line, I'll put in my checkpoints of 0 and negative 8. Now both of these are greater than or equal or less than or equal, so we are going to include the 0 and the 8. X could be greater than or equal to 0. So x could start at 0 and live anywhere above it. And then similarly, x could start at negative 8 or live anywhere below it. And so the solution set there is in two separate pieces.